Hello, folks. Welcome back. So, we have so far been working with the concepts of linear momentum and linear impulse, and conservation of linear momentum, and the principle of linear impulse and momentum. Not usually, sometimes I skip the term linear and I say just conservation of momentum. But note that everything we have discussed so far was about linear momentum. And linear momentum is, well, the velocity vector multiplied by the mass. Now we are going to kind of extend that concept into somewhat of a rotational domain. And instead of having linear momentum, we want to introduce the concept of angular momentum. So to see how it is going, let's consider a, let me draw the frame to make 3D movements more visible. So it is a particle randomly moving around in a space. Doesn't matter really what it is doing, but it has a velocity vector like this, and let's take the origin for instance, point O. I can define, let's write it here, define angular momentum about point O. So angular momentum, you always define it relative to a point. It is defined as angular momentum is the moment of linear momentum about that point. About point O. Let's see what we mean by moment of linear momentum. So if you remember from other courses like statics, we had moment of a force, and it was force acting at a distance. It is exactly the same thing, because this object that has mass m and velocity v, well, let me write it this way. It has linear momentum, that is this quantity, and because we are at a distance r from this point, the vector has a moment about point O, and that is what we call angular momentum. We use letter h, also a vector, and moment of a vector is the distance vector cross product by that thing. So in this case, we have vector of linear momentum. The moment of linear momentum is r cross that vector. And if you remember, again, a good analogy is the moment of a force. It was a vector in its general form, and that one is a vector like this that is perpendicular to both the r and to l vectors. So essentially perpendicular to kind of this plane that contains both R and L. And the direction is defined by the right-hand rule. So if you are not fresh on the cross product, I highly recommend going back and looking at the properties of cross product and what it entails, including the direction and how you find the final resulting vector. So this is the true definition of angular momentum. In other words, very loosely speaking, this angular momentum is I put it in quotation because it is kind of not exact. It is rotational effect of particles' linear momentum about your reference point. Even though there could be absolutely no motion, just a particle going along a straight line, because you are looking at it at a distance from reference point O, there is some rotational aspects to this linear motion, and that is reflected in your angular momentum. So again, very important, note here that h, angular momentum, is a vector. And its unit is, do I write it? Let's write it here. Unit of angular momentum is meters times kilogram meters per second. That is the unit of linear momentum multiplied by another meter. And that is kilogram meter square over second. A kind of funny looking, complicated unit, but this is the unit of angular momentum in SI, or its equivalent in imperial system. If you have I already mentioned this, that the vector of angular momentum, because it's a cross product, it is perpendicular to both the R vector and the L vector. When you are in 2D, so let me draw another three-dimensional reference frame. But my entire motion, this is not great, lies just in one plane, like in the XY plane. And this is my L vector. So here, to, for instance, find the, by the way, the reference point doesn't have to be O, it can be anywhere. Let me actually do that. Instead of O, I want to have another reference frame where, here, who cares? This is my new reference frame O prime. And I want to find the angular momentum about this new point. Well, not new point, O prime. What you can do, you have seen it. No, that's not a good location for O prime. Let's do here, O prime. You remember, to find the moment of a vector, you can do a vector from that reference point to your location, call it vector R, and calculate R cross L. Why does my L look weird? L. Or you could find the shortest distance, D, from the point to the line of that vector. And here you can find H. It is R cross L always. Always you can use this. Or it is norm of L times d, the shortest distance, the perpendicular distance, and the direction in this case, because I'm in 2D, I know the vector h must be, h must be perpendicular to both L and R, in the essentially perpendicular to the plane of motion. So it has to be either in the positive or negative z direction, and knowing from right hand rule that it is R cross L, let me do it with my finger, R cross L, it is about positive k. This is that. So you can also use geometry to simplify your calculations, but remember that always you can do cross product. As long as you know the vectors, you can do the cross product. Let me see if there is anything else I need to tell you. Oh, well, yeah, that's something I had in my note. I don't know why I wrote it this way. Let's do it this way. Norm of L is mv, right? mvd in the k direction. That's better. That makes a lot more sense. Okay, good. I think that is all I wanted to say. Yep. So now we have defined the concept of angular momentum. You can guess where we are going with it. We had the principle of linear impulse and momentum. Now we have the angular counterpart of momentum. So eventually we want to define the principle of angular impulse and momentum. That is what we will do next. So I'll see you in the next video.